All right, so welcome back. Welcome back to the channel. So, all the last few videos we have been learning about language modeling. In the last, I think in the last series we have done, we have learned about chat def to develop models that are we'll build an infrastructure in which many language models will combine together and perform different tasks of software development, and they combinedly this infrastructure that we could build, we could automate the whole process. If you are interested, maybe check it out. The last series, chat dev. I think I've done like 3 videos or something. Check out. So in this video, we are going to cover, I think, a pretty interesting topic, right? I think it's a relatively new paper. It's a it's a new paper that have, I think, released in 10th May 2023. I think it was released in 10th May 2023. Yeah, probably. So we are going to read this paper. So the main idea is to use LLMs, language models, for recommender systems, right? We will be using LLMs. So there has been a lot of hype. There has been a lot of demand, and there has been a lot of production of language models. Not only GPT, but there are many other language models. Even if you don't know about it, there are many language models that even you don't know. Let's say there is POM, there is Flan, there are just so many models that you could experiment with. And as these models are getting better and better, right, these models are leaving benchmarks. These are just setting records uh, in the language modeling field, right? So uh, since there has been this hype and this exponential improvement in language modeling, of course humans, we would, I mean, the best thing for us to do now is to use these language models for as many applications as possible, right? As there is so much potential for this field, language modeling, it's general to think how we could apply it for different other projects as well, right? Now a team from Google tried to use this language model, LLMs, for recommender systems, right? If you don't know what recommender systems are systems that recommend you content or recommend you different things based on your previous history, right? For example, maybe you must have probably visited applications like uh, you must have visited applications like Amazon and maybe Netflix, right? So as you go through these applications, and maybe you buy something or watch something, uh, these platforms, either Amazon and Netflix, will recommend you content or products that you might like, right? And most probably you will like it because uh, the things that you watch tend to have some type of features, and all the things that you like and watch and like tend to have some features, some hidden features maybe, or some known features, or something. They tend to have something that attract you, right? They tend to have something that attract you, um, and this feature could be determined or recognized by a language model based on the history of many users. So there might be some users that have similar tendencies to watch something, right? uh, Maybe there are someone similar, and so based on that we'll recommend you different things. Maybe that person likes other things, and it's a I think we build a huge system around this, taking inputs from different people and all that. um so right, so that's how recommender systems work. I have already made a video on recommender systems previously. So if you are interested, check that out. You may get a basic understanding of on what the classic recommender systems work. And you don't even have to have a very good understanding of recommender systems to understand this. If you are good at deep learning, definitely, if you understand language models, and if you can understand what NLP actually is, you could definitely go through this paper. And I don't think this could completely replace the current recommender systems. The current recommender systems are actually pretty good, but this might be a pretty good approach. As there has been a huge improvement in language modeling, we might use it, and it may work. It may be better than the other recommender systems. I don't even see a large gap in what these models are doing, but what the LLM, I don't see a huge difference between LLMs and LLM for recommended systems in this, as said in this paper, and the natural language recommenders that we use. But we'll go through this paper. Even I haven't had a very good look at this because I just wanted to read this paper before you. Right? I just want to read this paper before you. Even I don't have uh any any good idea about this paper also. But we'll go through this paper slowly. We'll go through this paper slowly, understanding each paragraph. I mean, even and not it's not very big, but I think we'll cover the most important parts that I think would be important. Even if you just see this, you could just easily understand what is important and what is not, just looking at the words and all that. So let's go through the paper. Um, let's read it together. So I'll just read it. I think I'll try. I'll read it pretty slowly. I think I'll try to make it as understanding as clear as possible. So let's get started. Right. So again, these smart people have built this paper for us to actually read it. They're like all from Google Research and Brain team. I think Google Brain or something, maybe dealing with AI. They're pretty talented individuals. So let's get started. Do LLMs understand user preferences? Evaluating LLMs on user rating prediction. Right. So the title is actually pretty understandable and pretty related, I think. Do LLMs understand user preferences? I think this is a pretty good way to formulate the problem of recommended systems, especially for beginners. Right. So, and can LLMs recommend content? I think that is a very high level title that may not be understood by many individuals, but this does break down the problem into, I think, a pretty slight step. Anyway, let's get started. So first paragraph, language models. As I've told you, language models have demonstrated exceptional capabilities in generalizing to new tasks in a zero-shot or few-shot manner. However, the extent to which LLMs can comprehend user preferences based on the previous behavior remains an emerging and still unclear research question. Comprehend user preferences based on their previous behavior remains an emerging and still unclear research question. Like maybe it is. I don't clearly see the problem, but as these are smart people, we should believe that the LLMs can't comprehend to user preferences based on their previous behavior. I think this is what the researchers are telling us, that they are telling us that LLMs cannot comprehend to user preferences based on their previous behavior. I think that this is actually quite a clear statement. Even I have experienced it. In past behavior will not be given quite huge importance. Maybe past conversations also. Traditionally, I'll start reading. Traditionally, collaborative filtering (CF) has been the most effective method for this task, predominantly relying on the extensive volume of rating data. In contrast, LLMs typically demand considerably less data while maintaining an exhaustive world knowledge about each item, such as movies or products. Pretty good point, right? So, recommended systems, they don't have any knowledge about the data. We have to train the model on the movie data. This is the ratings and the what people other watch, what people have watched, and what people have rated things. But these models know about the content that you are talking about, right? So let's say you want to buy like a let's say you bought a dumbbell, right? So let's say you bought a dumbbell, then you're most likely to buy let's say a cycle, right? Maybe you want to if you are buying a dumbbell, then you most probably are likely to buy a let's say cycle, right? So this information, this relativeness, in the case of like recommended systems, this relativeness, the relation between a cycle and dumbbell, right, is determined by previous users, right? So let's say a user bought a dumbbell and a cycle, then we could understand the recommended system. The classic recommended systems can understand that both of these items are related, right? Whereas LLMs have a huge understanding of the current world, how the world works, the different components of the world. Hence, this provides us an advantage right? Rather than using a lot of training data, the model knows about these movies and knows about these products, such that it could have an understanding to uh, predict the user preference, right? In this paper, we conduct a thorough examination of both CF and LLMs within the classic task of user rating prediction, which involves predicting a user's rating for a candidate item based on their past ratings. We investigate various LLMs in different sizes. Um, yeah, so we can just skip that. Introduction, we can also just go that, or maybe we'll try to read it fast. Language models have shown an uncanny ability to handle a wide variety of tasks such as text generation, translation, summation. The recent fine-tuning of LLMs on conversations and the uses of techniques like instruction fine-tuning and reinforcement learning with human feedback led to tremendous success to bring highly human-like chatbots to the average household. There are three factors that directly contribute to LLM's versatility and effectiveness. Knowledge from internet, scale, real-world information. LLM are trained on enormous data of text, providing access to a wealth of real-world information. This information is converted to knowledge that can be used to answer questions, creative writing, and translate between languages. Yeah, LLM is trained on enormous data. This is what the point I have been telling. They have a knowledge of the real world, on how the world functions and different relations in the world and different things that people tend to like. They understand people language models. And number two, the second factor, incredible generalization ability through effective few shot learning. Within certain contexts, LLMs are able to learn new tasks from an extremely small number of examples. Few-shot learning. Strong few-shot learning capabilities gear up LLMs to be a highly adaptable to new tasks. Right? Again, as these models have very high knowledge on the previous world, as these models are trained on very huge data, internet data, real-world information, these models can easily be trained or fine-tuned for a different problem. Right? For example, recently there is I have used Llama, right? We have Llama, right? Train on lots of data. I have used it for my CBSE data, my school data, and we could, and it would learn easily, like whatever task, let's say giving marks for each of the students' answers based on the question that is generated by AI. So let's say the AI generates a question and the students are made to answer it, and maybe the AI should give marks to it. Maybe for this task, we could easily train this model, as the model already has an understanding of how things work, right? Our model already have a high background information. Hence, we could easily generalize this models, and they have quite huge generalization ability, right? Strong reasoning capability. LLMs are able to reason through a chain of thought process, significantly improvement the performance across many tasks, right? They could chain of thought, right? They could have some reasons for they could just create reasons, right? For they have a strong reasoning capability, right? um right, in this paper we explore the use of the off the shelf large language models for recommender systems. We study a variety of LLMs of various sizes, ranging from 250 million to 540 billion parameters. We focus on the specific task of user rating prediction and evaluate the performance of these LLMs under three different regimes: zero shot, few shot, and fine tuning. Right, zero shot means I think zero shot means that we don't give any training data, previous data, maybe. I think that is zero shot. I mean, in this context, of course, zero shot. Normally, zero shot means that we just take a model belonging to, that's trained on generalized task, and we just use it for different specific tasks. But I don't know what it meant in this context, but we'll just carry on for now. Few shot, again, we have looked at it. We'll just provide some examples of of some data, and then fine tuning is we'll just take the model and completely train the model, right? Rather than just providing. So in few shot, we'll just provide the data as like prompt. We'll just provide a prompt for the model. We just provide the data as a prompt. Whereas fine tuning, we'll update the model's weights. We'll update the model's weights based on a specific problem or data set belonging to a specific problem. Right? We'll just go on. We'll just move on. Hope you have a basic understanding of what this means. So we then carefully compare them with the state-of-the-art recommendation models on two widely adopted recommendation benchmark datasets. Our contributions are threefold. We empirically study the zero-shot and few-shot performance of the off-the-shelf LLMs with a wide spectrum of model sizes. We found that larger models can provide reasonable recommendations under the cold start scenario, achieving comparable performance to decent heuristic-based baselines. We show that the zero-shot LLMs still fall behind traditional recommendation models that utilize human interaction data. Zero-shot LLMs only achieve comparable performance than two surprisingly trivial baselines that always predicts the average item or user rating. Furthermore, they significantly underperform traditional supervised recommendation models, indicating the importance of user interaction data. Definitely, zero-shot models, of course, they fail because they don't have human interaction data. They don't have any data. Zero-shot. I think that what it means here also, in this context also. We don't have any data. So therefore, as there is no human interaction data, they of course will fall behind. Compared to the traditional supervised recommendation models. Through numerous experiments that fine-tune LLMs on human interaction data, we demonstrate that fine-tuned LLMs can achieve comparable or even better performance than traditional models with only a small fraction of the training data, showing its promise in data efficiency. Quite good, right? We could fine-tune these LLMs on human interaction data, or let's say on previous data on what people watch and how they rated things, and we'll have some data, right? So when we fine-tune these LLMs on human data, we find that these fine-tuned LLMs are able to achieve equal, or these LLMs are able to achieve equal or even better performance, and are trained on only fraction of the data, on a very small fraction of the data, on very small part of the data. These models are trained, but still they are outperforming or even reaching the level of these supervised traditional recommendation models, and this is actually quite promising, right? Okay, so now everybody could build recommendation systems using LLMs, right? Related work, so they have shared some of the related work. Just check out if you are interested, right? So yeah, so I think they have just told something. We could just leave that part, the related work section, or maybe we could read it at the last. So we'll read the method, the problem formulation. We study the task of user rating prediction formulated as given a user a sequence of users use historical interactions, right? We'll be given a user, let's say an ID and all the history and an item. Predict the rating that the user U will give to the item I, where the user historical interactions with the sequence EU is ordered by time, right? Is the most recent one that we consume, and each interaction EUK is represented by information about the item, example ID, title, metadata, etc. So these features will be given for each item. Let's see each movie that the user has consumed, as well as the rating that the user gave to them. So we will be given several ratings that the user has given and an item, and each item will be given with the metadata, the title, the rating that the user has given, right? I think that's it. Or I think genre also, title, metadata, etc. Right? We'll be given this data, and each user will be having interactions, EU to EUN, and these are like these are ordered by time. So the first item is the first movie or first product that the user has bought, and then given an item, the model is asked to predict how much the user might give to the item I. That is a problem, right? Pretty simple. Might look zero shot and few shot LLMs for rating prediction. So let's go on to the next section. So I think what is this? Yeah, given users sparse movie ratings in the format, title, genres, rating from. So yeah, we'll be given I think these models, a movie name, a genre, and a rating, right? I think that format. And then the current will be given a new movie, the genre also, and the model is going to predict the rating that the user will give. All right. So whereas in few shot rating predictor, you're required to predict user rating. Shri in the format of the title. Okay. I don't see any I don't even see any difference here, but all right. So mm, all right. So I think here you are given the user's past trading history. All right, we'll just move on. I don't understand the figure yet, but we'll just move on. How we can formulate zero shot and few shot predictors. Let's just go on. We demonstrate that zero shot and few shot prompts use it for rating. Okay, okay. So let me get this. I have misunderstood this. So I'll just make it clear for you. So in zero shot predictor, we are only given the data of the current user that we are going to predict. So let's say we are predicting for a user U, and we are only given the data of the history of the user U, which we are just directly given the data of the history of the user U, the current user, and then we are giving the ratings and the genres and the content name, the title, and the model has to directly predict the user's rating for a candidate movie or candidate product. Whereas in few shot user predictor, we will be having the model. I will be giving the model different. Different. Like different. We'll be giving the model the different histories of different users. Right, we'll be having many users, and we'll be providing the model with examples. We'll be providing the model with examples. So we'll be providing the details like this. So we'll be providing the history, the user history of a specific user U. Let's say U1 will be giving the history of the user U1 and the rating that has given to a particular content, and then we'll be giving this history and this prediction for different users, for many users, such that the model can understand these examples and based on that predict for the new example. That is few shot, right? I think hope it makes any clear. Hope it becomes clear, right? Finally, okay, so finally, to elicit a number of numerical rating from the model, the model response is passed to extract the rating output from the model. However, we discover that LLMs can be highly sensitive to the input prompts and do not always follow the prompt provided instructions. Yeah, so we'll just add these text, give a simple number as rating without explanation, do not give reasoning. Just because we want the model to just predict the number and nothing at all. Sometimes the LLM may not even give the prediction. I mean, if you have used ChatGPT, you can understand. You ask it for an answer, but it just tries to get you to the conclusion. Giving you some very thinkable or very just giving you some text rather than giving an answer. So to avoid that, they'll just add something to the prompt. Right. All right. So we'll just move on. Fine-tuning LLMs for rating prediction. In traditional recommended system research, it has been widely shown that training models with human data is effective and critical to improve recommenders' capability of understanding user preference. Right. And again, understood. Right. Here we explore a training LLMs with human interaction and study how it could improve the model performance. We focus on fine-tuning a family of LLMs, namely FLAN T5, developed by Google, and again, as the paper is wrote by Google, since they are publicly available and have competitive performance on a wide range of benchmarks. The rating prediction task should be formulated into one of the two tasks: multi-class classification or regression. Right? In order to fine-tune the model, we have to formulate the problem into either multi-class classification or regression. Right? If you have any basic idea of deep learning, you know that the basic two problems that we are solving in deep learning is multi-class classification or regression, the basic problems. So in the case of multi-class classification, LLMs, either decoder only or encoder decoder architecture, are essentially pre-trained with a k-way classification task that predicts the token from a fixed vocabulary with size k. So the LLMs, the language models, remember the basics, remember the attention mechanism, remember the text generation task. We are just predicting we're just having a k-way classification. We're just having k tokens, the k possible words in the model's vocabulary, and we are just having a multi-class classification task. So we're just predicting one word out of the all the possible words. We're just predicting the next word. So LLMs are mainly multi-class classification models, right? So there is a projection layer that projects the output from the last layer to the vocabulary side. Then the pre-training optimizes the cost. The output logic is computed that loss decoder equals to W project, then HD decoder, whereas W project is I can skip that. We formulate the rating regression task as a 5-way classification task where we take the rating 1 to 5 as 5 classes during training. We use the cross entropy loss as another classification task and as shown below. Right, where RI is a ground truth rating for the ith item, and N is the total number of training examples. Right? How can I'll just try to explain the things that have right here. We come from model each output graph and choose a class with the largest probability of information. So basically, right? Basically, we'll be having an LLM. Let's say we'll have an LLM. Right, so the LLM is going to consist of, let's say, encoder and decoder architecture. I wonder if they use encoder decoder architecture is both, but yeah, and both are equal. I think yeah. So we will be having, we could either use encoder architecture only or encoder and decoder architecture. So what we are going to do is, while fine tuning, we will be having some real world data. Right, what we're doing is we'll be having some real world data, right? For fine tuning, we'll be using a fraction of the data that is used for recommender systems, classic recommender systems. And what we'll be doing is we'll be having the data, right? So the data is the inputs are the item. So the input is going to be the item. Let's say we are going to have an item called let's say one item one. We have input item one, and we are going to have an actual value, right? We are going to have the actual value that the user gave as the rating, is let's say number 5, right? And such that like this, and like this, we are going to have we are going to have data for all the models for for like all the content. We are going to have models. Data, and what we are going to do is, we are going to take this input and try to make the model to predict the output and update the weights as we go on, right? We'll just take the model's previous pre-trained weights, right? We'll be taking the model's pre-trained weights, and we would just try to update the weights of the model such that we could fit the model to this problem in which the input is in input content, and we are just making the model to predict the output, right? I think that is the main thing, right? Where R is the ground truth rating for the ith item, and N is the number of total training samples, right? For each item, we are going to have a rating, right? So based on this, the model could understand so let's just see again. Let's just read again, just to make it everything on just to make everything is clear. LLMs are essentially pre-trained which predicts as shown in okay. I think yeah. So there is a projection layer, the products that projects the output from the last layer to the vocabulary size. Then the pre-training optimizes the cross entropy loss for the token classification. The output logits is computed as logits DEC equals weight project HDEC, where double project is the projection matrix. Here the output of the last transfer layer DEC. All right. So what is our input? What is the input of the model? All right. So all right, I got it. So the input, right? So let's say we have an user. Let's say we have user 1. So let's say this is the training sample 1. So the first row, let's say this is the first row. I'm going to explain the content that is in the first row of the training data, the first example, training example. So we'll have the let's say we'll have different items. And like what is going to be the structure of the data? We're going to have an item, let's say item number 1 or content number 1. And we are going to tokenize all this content with some number, and then we will have the genre, like whatever the genre is, and we are also going to have the genre into like maybe like classes, maybe let's say, yeah, all let's say action, and maybe have maybe we have a rating, let's say 4, and we're going to have bunch of columns like this. So this is the input, this is the input, and the model is going to, the output is going to be, let's say we have the this content 3. So the output is going to be the rating, the possible rating for this 3. So the output is going to be the rating for 3 given this information. So we'll taking this information. We'll also be taking the current movie, the current thing, the current, the content, the what the content actually is, and based on this history, the model is going to predict the output, the rating for let's say the content number 3. So we'll be given the previous data, the previous relations, and based on that we'll be predicting for the number 3. That is the idea of fine tuning. We'll be having the same, I think, format. It will be having the same format where we have the content, the identity of the content, the title. Yeah, the title also I'll put in here. The title also, the genre, and maybe some other metadata, along with the rating that the user has given already. And based on this, we'll be predicting this. So this is just one row of the train data, and like this, we are going to have multiple rows, and not that much. I think we're going to have, I think, less rows maybe. So that is the idea of that is this idea of how we can use LLMs, or how we can fine tune LLMs for this problem of recommender systems. And then regression, we have the regression to enable LLMs for regression tasks. We set the shape of the projection matrix W to be D1, so that it will be only output day 1-digit logits, right? Again, now here we are just going to have like just I think we are not going to have predict a class either from 1 to 5, but we are only going to have integer, and we're going to use a separate loss function. I hope everything is clear. I think that's it for this video. That is the main part of this video. Again, to summarize, right? We have LLMs. LLMs are performing way better because LLMs have way much background knowledge. They have huge background knowledge. They know about the world. They know about the content that we are talking about. They also know about the real world, the world that we are living in. They have a lot of data. They are trained on a lot of data. So therefore, we could use these LLMs for different tasks. And these smart people from Google figured out that we could use these LLMs for recommender system tasks, and these models are performing way better. And we could train these LLMs on very small data and still outperform the classic recommender systems. Right? So this is language modeling for recommender systems. So hope you have understood everything, and I'll see you in the next one. Thank you.